Hello, Algebra 1. This lesson, Lesson 6 on residuals. These are the values that you can find to determine whether your line of best fit is a good match for your scatter plot of data. Take a look at the learning target. All right, here's your warm-up. You want to mentally calculate how close the estimate is to the actual value using the difference or subtraction. Take the actual value minus the estimated value for these 4 items. Do it as quickly as you can, mentally, not using a calculator. Okay, the numbers in red are the ones that I quickly mentally did, pretty much looking at your ones values and subtracting it that way and ignoring the decimal, maybe sometimes rounding. And then in blue are the actual differences. And so that's just a quick subtraction. Okay, this is the definition of a residual. You should pause this video and write this down in your notebook. The residual is the difference between the y value for a point in a scatter plot, so the actual scatter plot data, minus the value predicted by the linear model. So the linear model is the values that are on the line. And the lengths of the dashed lines in the figure are the residuals. So here you'd have your actual minus your model, and it would be a positive number. But down here, your actual minus your model would be a negative number. But the larger the residuals, then the least fit line it is. Okay, you guys remember the orange problem? So what you're going to do here is you're going to open up Desmos and you want to create a scatter plot for the orange data. Okay, so here's your orange data once again, your number of oranges and the weight in kilograms of oranges. You don't need to watch the video again. Once you put in your scatter plot, you then want to use Desmos to create a line of best fit. So if you recall, you need to use the plus button in Desmos and then type in the f of x key, which is your function key, and type in y1. It will make that a subscript 1. And then the tilde mark, because it's going to calculate the regression line, mx1 plus b. And if you type that in and enter, it will give you a line of best fit. That is your model. So that's your estimate weight. And what you want to do then is you want to plug in 3, 4, 5, each of these values into this formula and get your estimate weight. Once you have that, write those values all down. Then you can calculate the difference between the two, and that's going to be your residual value. Go ahead and work on that now in Desmos, pause it, and then when you unpause it, you'll see the estimate weight in kilograms put in for you from the model. Okay, so here are your values. In this column, we have the actual weight. So these are what the scale said for the individual oranges. And in this column, we have the estimate weight. This is based on our line of best fit. I'll just write down what that equation was. It was y equals 0.216x plus 0.345. So that's in slope-intercept form. We have our slope and our y-intercept. And if you plug in 3 into this equation, out pops the 0.993. All right, let's answer these 3 questions over here. Compare the weights of the box with 3 oranges in it to the estimated weight of the box with 3 oranges in it. So they really want you to compare this estimate to the actual. And we can see that actual is greater than the estimate. And if I do a quick subtraction, 1.027 minus 0.993, we end up with a value of 0.034. That's a pretty small difference. They're really close. All right, the next question. How many oranges are in the box when the linear model estimates the weight best? So which number of oranges is the model the closest, is the estimate column the closest to the actual. And I'm just going to kind of look through here. Ooh, look at this one for 6. 1.617 and 1.64. So that one is 0.23 off, really close. So 6 oranges. All right. And then it says, how many oranges are in the box when the linear model estimates the weight least well? Explain or show your reasoning. So now I'm looking for what we're going to call the residual, the difference between actual and linear, that's the greatest difference. And if I look through here, it looks like it's right here, 7 oranges. This difference is about 0.095 difference, so that's much larger, 7 oranges. On the next slide, we're going to find all of these differences, which we call the residuals, and plot them on a graph. Okay, for question number 7, it explains once again what a residual is. The residual is the actual minus the estimate or the model. And if the actual value is greater than the estimated value, the residual is positive. If the actual value is less than the estimated value, the residual is negative. So we're going to do this for 3 oranges. In 3 oranges, the actual was 1.027 kilograms, and the estimate using the model was 0.993 kilograms. If we go ahead and subtract them, we end up with our residual of 0.034. And that is the difference between the two. It's a very small number. In 8, we have to find the residuals for each of these points in the scatter plot. So for 3 oranges, all the way up to 10 oranges, and we're going to plot them all. Go ahead and do that on your own. You might have to switch back or rewind a bit to get all your numbers and plot them on your own, and then unpause it and see how you did. Okay, so over here we can see the residuals, and here's our scatter plot. Let's look at the questions now. 9, which point on the scatter plot has the residual closest to 0? So I can see right here it's when there's 6 oranges. What does this mean about the weight of the box with that many oranges in it? It means that the actual weight is very close to the model weight or the estimated weight. All right, let's look at the next question. How can you use the residuals to decide how well a line fits the data? Well, the answer in this has to do with the farther away the line is from each data point means the line is not as good of a fit as one that's really close to all the data points. So when the residuals are closer to 0, you have a better line of fit. One other important note here is when you're using Desmos, after you calculate your line of best fit using the y1 tilde mx1 plus b, it shows that equation of the line, and there's a little choice to click on plot, and if you do that, it will calculate the residual values and put a plot right there on your scatter plot of those residual values, which is a really nice feature of Desmos. Okay, on this slide, it's really the next 2 slides, you're going to take and match a bunch of linear models labeled A through F with a bunch of graphs of residual plots labeled G through L. What you're going to need to do is pause the video and write down, kind of going back and forth, or you can open the notes file until you've determined which linear model goes with which residual graphs. Then in question number 2, you're just going to look at the residual graphs labeled G through L, and based on those, determine which line is the most accurate for estimating. So which line fits its data the best, and then on the other hand, which line fits its data the worst. So kind of go through and pick of all the residuals which one represents the line of best fit and which one represents the line of least fit. Go ahead and we'll page through these, pausing where you need to write down your answers. Here are your graphs of linear models. So you're going to be comparing these to the next slide and trying to match them with the plots of the residuals. Here are your plots of your residuals. These you want to match up. So for each linear graph from the prior slide, you want to match to a residual graph. You will need to open your notes file so that you can do this more slowly. All right, here are the answers. So the linear graphs, A goes with K, E with J, etc. Now I want you to just look at the residual graphs and determine which one represents the line of best fit, then determine which one represents the line of worst fit. Pause it and make your decisions now. Okay, the best answer is probably G. You might argue that I or H are a close second or third, but G, they're definitely closer. They definitely spread apart as it goes further out, but if you look probably at all these average differences, this would probably be the smallest set of differences. Now when we're looking for the line of worst fit, the answers are probably J and L, or L. Both of these, you can see that they're close in the middle, but it really means that line was kind of tilted, where all of these values, the actual were greater than the estimate, and all of these, the actuals was less than the estimate. Likewise, the same occurs over here with L. So both of those are probably the worst fit. All right, go ahead and try this problem on your own. You can pause it now. All right, here's your answers. So what does Tyler's line of best fit look like? Well, all these actuals are greater than the estimates because all the residual values are greater than 0. That means the line is very low versus the scatter plot and probably could be a lot better. So how well does it fit? Not well at all. Raise up the line. Okay, here's another sample problem for you to go ahead and try. Pause it here. Okay, so with this one, we have a plot of residuals, and it says, what does Lynn's line of best fit look like in comparison to the data? So I tried to show you a picture over here, but the actual data is above the line and then below the line. So you can see here, if this is the blue is the scatter plot, the line of best fit, the slope is off. It really should be kind of flattened out a little bit or kind of turned down to make it look better. So it would have been better like this. But what was happening here with the first line that I had is that you can see the actual blue dots originally were above the line and then they were below the line. And that's what we see in the residuals over here. So how well does that fit? Not well either. The slope is off. You really want them to be evened and very close around 0, 0 for it to be a good line of best fit. That concludes the lesson. Go ahead and try the homework.